So let's continue on, and let's now prove the second part of the second derivative test. So again, we're assuming that our function has a stationary point at x0, so the derivative is equal to 0, and now we're assuming that the second derivative at x0 exists and is negative, is less than 0, and we want to prove that that shows that it is a local maximum. So, as I say, the argument is pretty much the same, just with some major tweaks, but those tweaks are all very simple. The complicated parts of the argument remain exactly the same. So this will be a nice recap if you struggled with the argument the first time. So let's call the value of the second derivative at x0, we'll call that n, now for negative number, so it's less than 0. And again, because this second derivative exists and is equal to n, we can just write out what the definition of the second derivative at x0 is. It means that the limit as h approaches 0 of f prime at x0 plus h. Now I've dropped a bit here. We should have minus f prime at x0, but of course we know that f prime at x0 is 0, so I've just gone straight ahead and dropped that. So we've just got f prime at x0 plus h over h is equal to this value n, which is a negative number. Now again, what we're going to do is use the definition of limit that we know must be true in order for this second derivative to exist to infer things about firstly the existence and the values or the signs of the value of the first derivative. So I've drawn a picture here. We're again imagining h on the domain axis here, and we're imagining this quotient that we're taking the limit of on the codomain axis here, and we know that the limit as h approaches 0 is this value n. We know, of course, that this isn't defined at h is equal to 0 because you can't divide by 0. Now, by the epsilon delta definition of the limit, this means that I can take any epsilon and there must exist a delta interval around h is equal to 0 such that everything in that delta interval apart from 0 itself is mapped into my epsilon interval. Now again, I'm going to set epsilon equal to a value that makes sure that the epsilon interval around n is entirely negative. So I'm going to take the mod of n and divide it by 2. So because n is this time negative, I need the modulus sign there. So I can do this. I can take n, I can take the positive version of it, which is the modulus, and then divide that by 2, and then I can set up this epsilon interval around n. And because this limit exists, I am guaranteed that there must exist a delta interval from negative delta to delta, such that for all the points in that delta interval apart from h is equal to 0 itself, all of them, if you look at what this quotient is, firstly it exists, and that's important. It's guaranteed to exist, and therefore the first derivative evaluated at x0 plus h for any of these h's in this delta interval must exist, and it's mapped into this epsilon interval here, so it exists and it is negative. So I've written this out again. So what I've concluded is that there exists a delta such that if you look at this delta interval from negative delta to delta and you consider any h inside that interval, subtract 0, so not 0 itself, then if you look at this quotient f prime at x0 plus h divided by h, this exists, so the derivative at x0 plus h exists, and this quotient's value is less than 0 because it falls in this epsilon interval around n, which is a strictly negative interval, so all the values in that interval are less than 0. And I can divide this up further, so if I consider an h in the interval from 0 to delta, then that's a positive value of h. So if this quotient I know has to come out as less than 0, if this is positive, that means the numerator must be negative, so I can therefore conclude that f prime at x0 plus h for h in this positive part of the interval must be less than 0. And similarly, if I look at the negative part of the interval, so from negative delta to 0, and I consider an h in there, now we've got a negative sign here, so in order for us to end up with this quotient overall being less than 0, this must be positive, because if it was negative, this thing would end up positive. So I can therefore conclude that f prime at x0 plus h for h is in this interval is greater than 0. So it's the opposite way round to when we were proving the first part of the second derivative test. So when we were proving this one, those came out the opposite way round to now. So now just translating what this means into a more intuitive picture. So I've now drawn my function f, so here is the interval ab on which f is defined. Here is graphically representing the function f. Here is my stationary point x0 where the derivative is 0, and I'm sorry that that line doesn't quite touch this, but imagine it does. And now what this says is that there is a delta interval around x0 such that if you look at the right part of the interval, so from x0 to x0 plus delta, the value of the derivative of the function there is less than 0. That's what this translates into on this intuitive picture. So the h interval has been turned into this interval from x0 to x0 plus delta here. And similarly, if you look at the left part of the interval, which corresponds to this, minus delta to 0, then the value of the derivative in that left part of the interval is strictly greater than 0. And then, of course, we know at the centre point, x0, we know the derivative is 0 there. And then finally, all we need to do again is apply the mean value theorem to this information, and we can conclude that this point x0 must be a local maximum inside our delta interval. So let's start by applying the mean value theorem to a point in the right part of this interval. So we'll take an x that's in the interval x0 to x0 plus delta, and we're now going to apply the mean value theorem going from x0 to x. So I need to again convince you that the function is continuous over the closed interval x0 to x and differentiable on the open interval from x0 to x. Well, I know that the function f is differentiable everywhere in the interval x0 minus delta to x0 plus delta. The second derivative has guaranteed the existence of this delta interval where the function must be differentiable, and that's the delta interval that I've taken here. So I know that it's differentiable everywhere in that interval. This interval is contained within that interval, and differentiability implies continuity. So it is continuous over that closed interval, and then it is differentiable on the open interval. So I can apply the mean value theorem going from x0 to x. So doing that, I get that the difference quotient from x0 to x is f of x minus f of x0 over x minus x0. And I know that this will be equal to the value of the derivative for some point that's properly in between x0 and x. So there will exist, by the mean value theorem, a point in between these where the derivative at that point is equal to this difference quotient. But I know that that point is going to be inside this interval here, and I know that the derivative of the function f for every point in that interval is less than 0, so I can therefore conclude that this difference quotient is less than 0, and then I just rearrange this to get that the value of the function x at x is going to be less than the value of the function at x0. So doing this, because x minus x0 is positive, if this quotient comes out as being negative, that must mean that the numerator is negative. So I can therefore conclude that f of x minus f of x0 is less than 0. Rearranging that, I get that f of x is less than f of x0. So what I've just shown is that if you take any point in the right part of this interval and you look at what the function maps it onto, it must be less than what the function is mapping x0 onto. Now all I need to do is do the same thing for the left side of this interval, and I've then shown that x0 is a maximum for the function in this delta interval, i.e. a local maximum of the function. So the left side of the interval now, so let's take an x in the interval x0 minus delta to x0, and now let's apply the mean value theorem going from x to x0. Again, it needs to be this way round so that we're going forward, because now x is less than x0. So I can apply the mean value theorem because, again, the function will be continuous everywhere over this closed interval and differentiable everywhere over the open interval because it's contained within the interval from x0 minus delta to x0 plus delta, over which the function we know is differentiable. So the difference quotient then going from x to x0 will be f of x0 minus f of x over x0 minus x, and this will be equal to the value of the derivative of the function for some point from x, between x and x0. That's what the mean value theorem tells us. We know that the function its derivative is always going to be greater than 0 in that realm because that's contained in this interval from x0 minus delta to x0, and therefore I can conclude that this difference quotient must therefore be greater than 0. Then, because x0 minus x is always a positive number, if this quotient is going to come out as a positive number, I can therefore conclude that the numerator must be a positive number, so f of x0 minus f of x must be greater than 0, and then just bringing the x0 onto the other side, I get that f of x0 must therefore be greater than f of x. So therefore we have done what we needed to do. I've shown that if you take any x in this delta interval that isn't x0 itself, that the value that it's mapped onto by the function is going to be strictly less than the value that the function maps x0 onto, and therefore x0 is a local maximum over this delta interval for the function. So we've shown, therefore, that the second derivative at x0 being less than 0 implies that there does exist an interval over which the x0 point is a local maximum for the function over that interval. So we'll have a break here, and in the next part we'll move on to looking at proving the partial converses here.